In this video, I'm going to discuss how we can fit data to an Ising model using Pyfolding. So as per all my other videos, let's start by opening Jupyter Notebooks. And if we navigate to our Pyfolding folder and go to our notebooks, you can see we have these three notebooks here which describe in detail how to do so. But let's look for this video on how to do it for the heteropolymer Ising model. And again, as with all my videos, I'm going to show you how we do this by copying the relevant commands to a new notebook so that you can see how it all fits together. However, if you read carefully or have a notebook open while you're looking at this video, you can see exactly how we're doing it, and there'll be more explanation if you read carefully our comments and how we've annotated our notebooks. So as per always, let's load in Pyfolding to start with, where we're also loading in our models, and specifically our models to do with the Ising model. We're going to need some data, and here I'm going to load, because the way that the Ising model works, we need a whole series of data sets where we can change the data sets per changing of the modules which are present in the protein. So in this case, I am using data from our 2016 JMB paper, where we looked at a series of CTPR proteins where we made helix deletions and helix insertions. So each one of these data sets is the chemical denaturation of one protein which has differing numbers of helices. So first off, let's load all the data into Pyfolding. This is our path, and these are our data sets where we're leaving them in as equilibrium data, and we're going to make a Python list for each of the data sets. I'm going to set the temperature, because all these experiments were done at 10 degrees, and we're going to plot the data to make sure that everything is as we should expect. So this code here plots the figure and tells it to plot all our denaturation curves. And you can see this is them all here, and it's fraction folded by denaturant concentration, and this is each of our curves going from our smallest proteins with least helices to our proteins with most of helices. So let's print out the information on our heteropolymer Ising model. And what you'll see is that the way the heteropolymer Ising model is defined is that it has a partition function which includes terms for the intrinsic stability of each folding unit and an interface energy, how those units interact together to make the fully folded protein. What that means is that, defined by the topology, each curve has a different equation which actually fits it, although all the parameters are shared between all the equations and all the denaturations. And the great thing about Pyfolding, the way that we've coded it, is that if we can graphically determine and decide our topology for each of these curves, and for the protein which produces these curves, and Pyfolding will solve the partition function and enable and produce the equation for each of these curves without you having to solve each one yourself, which is really, really cool. How we define the topology is that in Pyfolding we have coded in a whole bunch of generic types of domain, which we have defined with certain names which are all relatively, I guess, they could really be called anything, but we decided to call them that, these names here, and you can read all about them in our notebook. But basically, each motif in general has an intrinsic stability term, a denaturation dependence, an interface term, and this is for each one except for the cap motifs, which we do not print their interface term. So the cap should only be used on C-terminal deletions. So what we can then do is we can go in and we can shorthand what each domain is, and then we can define a whole bunch of topologies depending on the proteins which make up our denaturation curves. So in this case, it all goes from N to C, where you have, in this case, for our first protein, which is CTPR2 without an helix, which has 4 helixes in general, we have 3 types of them. And then what we can do is we can plot out and save, if we wish to, these topologies in a graphical form. So these are all our proteins. These are the topologies that we've given them. And then we can plot our results. Well, we cannot plot our results, but we can fit all our data to all our curves and the topology 1 that we defined up here. Now, I'm not actually going to run it in a notebook because it takes quite a long time on my slow Macintosh, but suffice to say that after a while it will find global minimum, and it will give you on a per protein basis what all the parameters are, and obviously that they're shared. And it will also print out the topology that you've used, the curve fit to all the curves you fitted it to, the first derivative as a fit of the function, and the fraction unfolded of each of the repeats as a function of ground name as well. And you can try a whole bunch of differing topologies depending as you see fit, and it will show you the curve fits to them.